Up until now, we've looked at discrete instrumentation amplifiers. In other words, ones that you would build with individual op-amps and individual resistors. But the last part of this lecture is going to look at monolithic instrumentation amplifiers. In other words, ones that are built all together on the same chip. Let's look at the two. So a discrete instrumentation amplifier is limited by the amplifier common mode rejection ratio, the output stage, resistor matching. But monolithic instrumentation amplifiers can do clever things. They can match the common mode rejection ratio of the input amplifiers because they're on the same chip and they always know the performance of them. The monolithic instrumentation amplifiers can also trim the resistors to make sure that the resistor match is much better. And finally, within monolithic instrumentation amplifiers, the offset voltage can be trimmed to match. It doesn't need to be trimmed to 0 because it nulls out from the circuit, but you can trim both input amplifiers, op-amps, as a pair and get them to match each other. And in many applications, when you want high performance, the monolithic instrumentation amplifiers can actually be cheaper and better performance than the discrete ones that you might want to build. Before we go and start looking at the detail of monolithic ones, I want to talk a little bit what do they look like. So I found a micrograph of an instrumentation amplifier. And in this analysis here, we can see two large areas of resistors that have been very carefully laid out and very carefully matched. I would encourage you to read the full paper, which I've uploaded onto Moodle, to find out the detail of this instrumentation amplifier design. Let's compare a monolithic design of an instrumentation amplifier with a discrete design of an instrumentation amplifier. In other words, one that you would build yourself out of discrete op-amps. We have here a instrumentation amplifier circuit, and on the left column we have an OPA 177 plus 0.1% resistors for the difference amplifier, and on the right we have an INA 131A, which is a monolithic amplifier. And I've uploaded the datasheet of the INA 131A to Moodle so you can look at the details of the amplifier and how you apply it. I've compared several parameters of the performance here, and let's go through these one at a time. First of all, offset voltage. So on the discrete solution, we get 120 microvolts, which is 60 microvolts from each of the input amplifiers. But on the monolithic amplifier, we get 125 microvolts, slightly worse. On the bias current, on the discrete solution, we get 2.8 nanoamps, whereas on the monolithic solution, we get 5 nanoamps. Again, slightly worse, and we may wish to choose our discrete solution for that. But now let's look at the common mode rejection ratio. For 0.1% resistors, we would get a common mode rejection ratio of 94 decibels, but the monolithic solution would get a common mode rejection ratio of 110 decibels, almost 5 times higher than the discrete version. In the gain error, if we only have 0.1% resistors around the difference amplifier and 1% resistors for RA and RB, we would get a gain error of 2.2%. But if we replace the resistors around RA and RB by 0.1% resistors, then we would have a total gain error around the discrete solution of 0.4%. In the INA 131A, we would land up with a 0.1% gain error, so considerably better there. If we look at gain error drift, which is the change of gain over temperature, in the discrete solution it could be 130 parts per million, whereas in the monolithic solution it's reduced down to 20 parts per million. And the final point is the price. If we have only 0.1% resistors around the difference amplifier, the price for our discrete solution is £7.73. whereas the INA 131A is £5.19, so considerably cheaper for the monolithic solution. And if we were to replace all the resistors around the discrete solution by 0.1% resistors, then our price for our discrete solution would rise from £7.73 up until £10.50. So considerably different, and in fact our discrete solution here is almost double the price of a monolithic solution, and yet the performance is comparable or worse than the monolithic solution. And there are other benefits by using a monolithic solution, such as the area on the board, the power consumption, the common mode rejection ratio, performance versus frequency, and many others. I would encourage you to look at the datasheet and consider where a monolithic solution would be a better solution than a discrete solution. Now let's look at some general instrumentation amplifiers and where they would be good and ones you can apply for general purpose. So first two is INA 114 and the 131, has a performance or an op-amp performance which is very similar to the 177, but has better dynamics. If we move on to the INA 111, it has an exceptionally good FET front end input stage with a very low bias current down to 2 picoamps. The 105 and the AMP 103 has got exceptionally good resistance matching and can achieve 0.001% matching. I would finally draw your attention to the AD8429. Now, while this is actually a very good instrumentation amplifier, it has been optimized for audio applications. Indeed, it's been optimized for microphone preamp applications. It has got a very high bias current, it's got a very low noise, but its gain bandwidth may be quite limited. So this is an example of an amplifier that is a special application, and you should only use it for the application it's designed for, because it may not perform that well in other instrumentation amplifier applications. Finally, we'll finish off with a couple of examples for instrumentation amplifiers. And here we have an instrumentation amplifier detecting the current flowing through a motor that's being supplied by a 0 to 5 volt supply. This motor impedance is about 4.9 ohms, and the question is, if the common mode rejection ratio error can only be 1% of the maximum current, what is the required common mode rejection ratio of the instrumentation amplifier? Let's do some simple analysis and do some voltages around it. If we have the input voltage Vs of 0 to 5 volts, that would suggest at the top end, at the non-inverting input to the instrumentation amplifier, a voltage from 0 to 5, and because this current dropped by the motor over the 0.1% over the 0.1 ohm resistor, it would give us to 0 to 4.9 volts at the negative input of the instrumentation amplifier. At a 5 volt supply voltage, our differential voltage at the input of the instrumentation amplifier would be 0.1 volts, but the common mode voltage would be 4.95 volts. If we only allow a 1% error in the current that's flowing through the 0.1 ohm resistor, that would dictate a common mode rejection ratio 73.9 decibels. If we assume that the output stage has a common mode rejection ratio of 54 dB, in other words, we're assuming that it has 0.1% resistors, then we require a minimum input gain of 20 dB to give an output of 1 volt for a maximum current. However, if the output could be increased to 10 volts instead, then the gain of the input stage could be increased to 40 dB, in other words 100 times, which would make performance even better. And we could then relax the specification for the difference amplifier to only use 1% resistors, because we've brought it back in the gain of the input amplifier. When you're making these decisions, always remember about the effect and impact of the common mode and differential input signals to the instrumentation amplifier. Make sure that the output voltage from the instrumentation amplifier is not driven into clipping. In other words, it would hit the supply rails because the signal would be too large at the input. And think of the impact of both the common mode and the differential circuits. We could draw the previous circuit in a slightly different way. We have still the same supply voltage going from 0 to 5 volts, but in this instance we've placed the motor above the sense resistor, the 0.1 ohm sense resistor. And now the instrumentation amplifier is operating between 0 volts and 0.1 volts. So we've reduced considerably the common mode input voltage. In fact, it's now only 50 millivolts compared with 4.95 volts before. However, making these changes, although they appear quite simple, may impact the application. And if you were to consider a change like this, you should speak to the customer, because, for instance, in the case of an automotive manufacturer, they would not want you to place the motor above the sense resistor, because the motor would be grounded to the chassis of the car and you would not be able to make that change. We've now finished instrumentation amplifiers, and I hope you've discovered how useful this circuit actually is when being applied to sensors and low voltage signals. Thank you very much.